So in this lesson, we are going to discuss about the cryptography pillar. So we'll discuss what are the major players inside the cryptography, and then we'll look into something called hashing, which is a subset of cryptography. And then we'll try to get into the modern hashing algorithms like SHA-1 or SHA-256 or any hashing algorithms like that. Now, without further introduction, let's get into the topic. So cryptography. So like I mentioned, it's a pretty big topic and we are not planning to cover even 10% of it. All we are going to do is getting some idea around how these things work. Basically, some kind of intuition we are trying to achieve. In fact, we are not planning to discuss any algorithm in detail such that it works in the modern world. But we will get some intuition about a couple of things. So one of the things we will be discussing is hashing. So one of the reason we will not be discussing in detail is the complication about the modern algorithms. Probably something like SHA-256. This is a hashing algorithm which we use in the modern day in a daily basis. Probably to explain how SHA-256 works, we need a training by itself. Another thing worth mentioning is that although we'll be discussing these algorithms, we'll not be discussing how it is used in the modern security landscape. That'll be coming in the later lessons. In fact, you will get to know that only after watching the entire training. So you will be wondering, what is the use of this thing? It looks fairly straightforward. What's the use? But you will get an idea. I'll try to build that intuition over the period of time. But you have to be a little patient regarding the usage of these things we are going to discuss. Being said that, first we are going to discuss hashing, what really it is. Then we'll discuss symmetric encryption or simply encryption. So encryption. I'm going to call it symmetric encryption or S encryption. Again, very straightforward to understand. Just like hashing, it's also very straightforward to understand from an intuitive perspective. Another thing we will be discussing today is asymmetric encryption or RSA. So this is not straightforward. There is a little bit of math involved, even to get the intuition. Otherwise, it'll be looking like a magic to you. So my plan is to give some trivial algorithms to make you understand these two things right here, hashing and encryption. I can give you a trivial example. But even to give trivial example for this one, things are pretty tight. So we will be going through the RSA algorithm to get a feel of it. It'll be a little more rigor, or it'll be a little more rigorous than these two items in the list. So RSA will spend more time to understand and get a feel of how things are done. There is one more thing called salting. Salting is probably the most straightforward out of all three we have discussed. It is nothing but adding a random number, mostly to the data you're hashing. So out of the cryptographic landscape, these are the things we will be discussing. These are the things we need to keep things going. And we'll be sticking our discussion to these four items. Mainly, we'll be spending time on these three items. Salting is just very trivial, just adding random numbers to juggle things out. That's what salting is. Let's take the first guy out of the picture, which is hashing. Before we get into the details of hashing, I want to reiterate the importance of this particular pillar we are discussing. So this is not something like black hole thermodynamics or anything like that. This is something we use in a daily basis. When you make a phone call, you use encryption, like I mentioned in the very first introductory lesson. So there is a mobile tower here which transmit data, and you have a cell phone right here and you are standing right here. Your friend is on the other side with another cell phone. Both are connected to this particular tower when you communicate. And all the information from this tower, the antenna or the tower, is a broadcast. Both of you are getting the exact same carrier signals, because antenna can only broadcast. It cannot do point-to-point communication. There are antennas which can do point-to-point communication, but that's not the point here. It is a broadcast. Now, the only thing which makes you different, let me draw that in a different color. The only thing that makes you different is the encryption. The data is encrypted coming to the devices. That's why you are not able to listen to someone else's phone call. Normally, we don't even worry about hacking that thing because symmetric encryption is pretty strong and pretty powerful. There are theories which proves mathematically, the rigorous proof says that symmetric encryption cannot be broken. It is not true for anything else though. Hashing can be broken, RSA can be broken, all those things are different. But symmetric encryption, there are theories, mathematical proof, formal, rigorous proof that this cannot be broken if you done it in certain way. Now, what I wanted to emphasize here is this is something you use in your daily life, everyday life. When you make a phone call, when you access your bank account, when you watch Netflix, YouTube, make a YouTube video, even when you are listening to this particular training, you are using what we are going to discuss. The world depends on it. Your privacy depends on it. Pretty much everything you see as of today depends on what we are going to discuss. Any break in these algorithms which we are going to discuss is going to be catastrophic. Being said that, let's get into hashing. So hashing or hash, the idea here is to represent a data. It's like naming a chunk of data. You can think of it like that. We are going to give an identity to a bit of data you're having. Just like your name, your full name with your date of birth and address. It's very difficult to have someone exactly same address, exactly same date of birth, and exactly same name. You can think of that combination is a hash of you. So let's take the example. This is you. And there's another person here in another part of the world who has the exact same name. For example, Anand George. So this name is pretty common. But when I add my date of birth, the number of people who has the exact same name and date of birth reduces. Probably there could be one or two guys who has the exact same date of birth as me and exact same name. It could be possible. Now, what are the odds they have the same address as well? That's impossible, almost impossible. So we can say that this is a hash of me. This is a unique piece of small information, which directly points to me and makes me different from anyone else in the whole world. My name, full name, plus date of birth, plus address. Very unique. So think about creating something like that for any data, any number for that matter. So that's the idea of hashing. Now, the problem with this is that in the case of human, like me or you, the number of possibilities are limited. But when it comes to data, there is infinite amount of possibility, which means that there's a chance that there's a guy who has exact same name and exact same date of birth and exact same address, because the collision domain is pretty crowded, unlike in the case of human example, because data can be huge and literally infinite number of combinations. But the idea remains the same though. Hashing is a representation of a piece of data. It's like identity of a data. So a couple of things to notice here is that this particular information right here, Anand George plus date of birth plus address, is a small piece of data. I have a lot of other attributes. I have my trainings. I have my bank accounts. I have my email. Everything is connected to me. My whole data or whole information within me is way higher than this particular piece right here. So that is one attribute. The data is always bigger than the hash. the data we are trying to represent is always bigger, much, much bigger than the hash. That's always the case. Another thing is that the one-to-one mapping, like I mentioned before, there should not be any other guy with this particular hash. If there is another guy with this particular hash, then it is called hash collision. So there is another guy right here, which has exact same name, exact same date of birth, and exact same address. He's just something like my twin brother living with me with the same name. Then there is problem. There'll be problem in the airport, problem in the identity. There'll be a lot of problems. Same thing in the real world as well. When you have hash collision, especially in the cryptographic sense, it's a security breach. If any of the modern hashing algorithm like SHA-256 or anything like that, if you're finding a collision, a deterministic collision, it means that that hashing algorithm is broken. It has a lot of implication, and we'll ponder through that implication throughout this training. But that's the idea of hashing. Now, what we can do is we can discuss a very simple hashing algorithm. So the simplest form of hashing algorithm is just the modulo operator, mod. If you have seen my previous trainings, especially the Python training, you should be familiar with this particular concept, the modulo operator. Nevertheless, let me explain. It is pretty straightforward. So you have a number here, say for example 11. When you divide 11 with say 2, the remainder is 1. We are not bothered about the quotient or the result of the division. All we are interested is the remainder. What remains, that's what we are interested in. Now 11 divided by say for example 8, what remains? The remainder is 3 in this case. So we can say 11 mod 2 is 1. So this is the mod operation, and 11 mod 8 is 3. Now the idea here is that 3 is a small number, depends on this particular value. 3 is always less than this particular value. We can limit this particular number, the output, by adjusting this particular value. And at the same time, it represents 11 in certain ways as well. So 3 has almost all the properties we discussed. It represents 11 in this case, and it is a small copy of 11 in this case. Now you must be asking, there are other numbers which can have the same value. For example, 19 mod 8. 19 mod 8. That's also 3. So 8 into 2, 16. 16 plus 3. The remainder of the division is 3. 16 plus 3 is 19. Let me write that calculation here because it's a fairly big number. 16 equal to 8 into 2. 2 is the quotient, plus 3 equal to 19. So this is the calculation. So 19 mod 8 is 3, which means that we got same hash for two different data. So this is our data. Let me take a different color. So this is our data right here, and this is the corresponding hash. We are trying to represent this big data with this number, and we got a hash collision. This is called hash collision. So we have different data and we have same hash. Two Anand George living in exact same house with the exact same date of birth and exact same address and exact same name, of course. So that's what this 3 is representing right here. Why this is happening? Because mod is a very naive hashing algorithm. Mod is not a very strong hashing algorithm or even efficient for that matter, performance wise. One of the things you can do is this particular number right here. We can have that as a very large prime number, a prime number with, say for example, 10,000 digits, a prime number with 10,000 digits. Think about that. Then your collision domain increases exponentially. So that is a more powerful mod operation. if this number is a large, very large number. It doesn't have to be a prime number, but normally prime numbers are used in this kind of things. So if this is a large number, again, this particular hashing is going to be more powerful. The collision is going to reduce. But then the compromise is that the data gets big, the hash gets big, and we need to calculate the calculation efficiency. To calculate 10,000 digit number, we cannot use simple calculators and things like that, so it gets complicated. So we need to be efficient, we need to be smart, we need to make sure that things are not overly complicated as well. So that is where all the modern hashing algorithms comes into the picture. We will be seeing some of them in the practical session of the cryptography using OpenSSL. We will be computing hashes, cryptographic hashes of some files and data and things like that. But the idea remains the same. To avoid collision, that's one of the reasons, the compute must be practical. Compute must be practical, and it should work for pretty much any kind of data. That's the idea behind hashing. Hashing is used everywhere. Code signing, signature, digital signature is all about hashing and encrypting that hashing. We'll discuss this in detail, how this is achieved. Another is saving passwords. For example, you might have heard your password is broken. Your password has been compromised. Google is giving that update. The Chrome is always giving that update. This particular password is compromised. Someone else has it because you have given the password somewhere and it was saved in plain text and it was not hashed. So saving password. So the password is this particular data right here, and to store it, you need to hash that password. So you'll be saving this particular 3 instead of 11. 11 is your password, but you are storing 3. How it works then? Who will remember 11? No one remembers 11 other than you. All we check when we check the password is the password you are giving when you do mod 8, whether you are getting 3. That's a check you are performing. We'll see some of this detail in future, but password signature is used in password, or hashing is used in password saving or storing passwords, or any secret for that matter. Not all the secrets are saved using hashes. Some of the secrets you need to get it out. For example, the AWS secret manager. In that case, hashing is not the way to go because you need to get back the exact data. If you save it as 3, you can never get back 11. Only you can check if the user is providing 11 or not. That's the only thing you can check, provided there is no hash collision. If there is hash collision and the attacker knows you are using mod 8, even though he doesn't know the actual password, which is 11, he will provide 19 and mess you up. You will get 3 and you will let him in because the hash is broken. So that is an attack to a hash algorithm which is not performing correct. A broken hash algorithm. As you can see, these attacks are not that complicated. We already discussed just one possibility of getting attacked when you use a vulnerable hashing algorithm. Now, another use of hash, probably the most familiar use case, is the SSL TLS. To verify the certificate, the signature, we use hashing algorithm. We'll get into the details, and in almost all cases, for example, signature, SSL TLS, we use a combination of the cryptographic algorithms we discussed. The symmetric, hashing, the asymmetric, which is the RSA, kind of the combination of all these 3 we use in almost all cases to optimize, to make things efficient, computable, and things like that. It's all comes to practicality at the end of the day. So what is hashing again? Let's summarize what we have discussed. Hashing is representing a data with a small number. That's the idea. The data is pretty big, but that data should be uniquely represented by a small number. That's the idea we are trying to get at. And if there is another data which has the same hash, we call the hash is broken or there is collision. That's what we have seen here. What is the reason for collision? The reason for collision is the weak hashing algorithm. The hashing algorithm is weak. A weak hashing algorithm cannot be used for cryptographic purpose. There are other purposes for weak hashing algorithms. For example, MD5. MD5, you can search if you want. Don't think we will discuss MD5 too much in this training, but probably we will see some samples of MD5. But MD5 is a broken hashing algorithm. It is broken around 1990s or something like that, but it is still used for certain purposes. Non-cryptographic purposes, MD5 can be used because it's very efficient and fairly straightforward than SHA-256 and things like that. But otherwise, these days we use SHA-512, 256, etc. By the way, cryptocurrency use all these things. I will restrict my discussion from cryptocurrency. Probably we will have a session on cryptocurrency in this training, but will not discuss too much cryptocurrency unless you guys have some questions. But one thing is that if you pay attention to this training, the moment you finish the training, you will understand cryptocurrency by itself. You don't need any additional information to understand cryptocurrency. Long story short, cryptocurrency uses all this kind of hashing, asymmetric encryption and symmetric encryption to make things happen. So if there is collision, the hashing algorithm is broken, like MD5, real world example, and we cannot use it for cryptographic purposes. Another thing with the hashing algorithm is that it should be computable. It should not be like 10,000 digit mode on a prime number. It's very difficult to calculate for a data. It may not be efficient. It'll be CPU intensive, memory intensive, doesn't work. So that's another criteria for hashing algorithm. It should be computable. Examples are SHA-256, 256. We'll see SHA-256 and then SHA-512. Before we wind up the hashing session, let's have a quick look at the Wikipedia page of hashing, just to make sure that we have covered some of the details we need. So this is the page, the Wikipedia page for hash function. Hash function is nothing but the function which does the hashing, the operation, if you will. Hashing is just an operation like addition, multiplication, or division. Mode is a typical hashing, simple hashing. Probably the formal definition of what we have just discussed. As you can see, there is key, which is the data, and there's a function right here, which is the mode in our case, the simple example we took, and you're getting the hashes, unique numbers. And there is this collision right here. The red one is a collision. So John Smith and Chandra D, they have a collision at 2. So that is hash collision, which is not good. So non-cryptographic hash functions, they are very useful. They cannot be used for cryptographic reasons, but they are useful for other purposes. So if you want, you can open it up. So like we discussed, the rigorous security requirement is not required. They are used for other purpose. MD5, I would say, it's a non-cryptographic. It was used for cryptography before, but not anymore. These are strong ones. They are the ones we are interested in. SHA-0, SHA-1, SHA-2, SHA-3, all these are cryptographic hash functions. If you want to delve into the mathematical details, you can click on one of these ones and go into any depth you want. So these are the algorithms, operations performed. And cryptanalysis, this particular word we will see a lot. Cryptanalysis is a method or a branch of mathematics. Like cryptography, what it focuses on is to find problems or vulnerabilities in the algorithm. For example, in the case of a hashing algorithm, what cryptanalysis is trying to do is to find a data which has the exact same hash collision. Find out a collision in a hashing algorithm like SHA-256, for example. So that is the branch of mathematics. Very interesting area of focus. As you can see, there are so many different attacks can be performed. Birthday attack, pre-image attack, and things like that. You can read about it if you're interested. But from our perspective, this is all we need. So feel free to have more information or read around it, but I guess we have discussed what is needed for hash. Next, we'll discuss symmetric encryption. So we have seen the components of cryptography or different topics inside cryptography, as well as we have discussed the hashing, one of the important cryptographic algorithms. It is used pretty much everywhere, from certificate signing, digital signatures, we will see that. Then cryptocurrency, pretty much everywhere, digital signatures as well as hashing is used. So it's a very important algorithm, and we'll see how that is used in the subsequent lessons. Thank you for watching. See you in the next.